Chapter 6, Electromagnetism and Electronics. So the chapter 6 of in this chapter we'll see about electromagnetism and electronics. Okay, to start with the first 6.1, Coulomb's law and electric field. We start from electric charge. Electric charge is an inherent property of matter that makes it to have an experience electrical and magnetic interaction. So it is one of the inherent property of matter. The effect of electric charge is observed when electronic devices are activated with a click of a switch, like computer, cell phones, television. So all this operated because of the presence of the charge. So and also it is seen in natural phenomena during heavy thunderstorm as a flash of lightning. So there are two types of charge. The first one is positive charge, the second one is negative charge. So as you can see here, these are electric field lines. Then the direction of these electric field lines found by using a test charge. So when a test charge is a small positive charge. So when the small positive charge approaches this other positive charge, so the direction of force is outward. Because of that, we can align the direction of electric field lines. So here in this one we have a voltage source and let's say a bulb. So the conventional current flows from positive terminal to the negative terminal, but electrons flow from negative terminal to the positive terminal. So this is the current. So whenever we say the current, it implies that the charges are moving. So current is equal to the rate of change of charge. Okay, so as you can see here, these are the model for flow of electrons from the negative terminal then to the positive terminal. So the change in Q over change in time is equal to current. Okay, now let's proceed to the types of charge. Many experiments in the past, including the traditional Coulomb and Hare, have revealed that there are generally two basic types of electric charge in nature. These two types of charge are, first one is positive charge, second one is a negative charge. So the charge is a physical property. We know that there are different types of electrical property, optical property, magnetic, blah blah. So among these, the charge is a physical property of an object and is a measurable quantity. It's a measurable quantity. The SI unit of charge is Coulomb, and the symbol for the charge we use Q, capital Q, or it's possible to use this small q. The smallest amount of charge to be carried by a material is the charge of electron. Its amount is 1 electron, which is equal to 1.6 times 10 raised to minus 1990 Coulomb. So this is the smallest amount. So whenever we say current, so a number of electrons is moving, so we can find the total charge by multiplying the amount of charge, which is for 1 electron we have this amount of charge. If you have 100 electron, 100 multiplied by 1.6 times 10 raised to minus 90 Coulomb. Okay, let's proceed. Okay, so the interaction of electric charge is governed by the following basic law of electrostatics, which states that we have like charges, they repel each other. As you can see here, this is a negative charge and this one also a negative charge. So it shows that these two charges repel each other. So like charges, like this one, if you have also positive charge and positive charge, they also repel each other. The other one is alike charges attract each other. This charge, the first one is positive charge, the second one is negative charge, so they attract each other. This lines shows actually the attraction between the two charges. So the field lines, this is for positive charge, it is outward, for negative it is inward. Okay, so the Coulomb's law and electric field. Experiments with electric charges have shown that two objects having electric charge exert an electric force on each other. That means if you have Q1 and Q2, negative and negative, one exerts the electric force to the other. For example, on Q1, Q2 exerts a force on Q1, therefore we can write force 1 by the charge Q2, and this force also by the charge Q1. Since these two charges are like charges, they repel each other. The force is in opposite direction. So here in this case, this is a negative charge and this one is a positive charge, and this is F12 by charge 2. The force is towards each other, shows they repel with each other. So force 12 is directly proportional to the multiplication of the two charges, and it's inversely proportional to the square of the distance between them, the square of the distance between the two charges. Okay, so the proportionality becomes equality with the introduction of proportionality constant. Therefore, the magnitude of electric force between two electrically charged particles F12 is equal to the constant Q1 Q2 over R square. This R hat is actually the direction indicator of force 12. So the R hat is different for in case of F12 and in case of F21, sorry. R hat in case of F12, this one, but in case of F21, the R hat, which is direction indicator, because they are in opposite direction. F12 is different from F21 in direction, not in magnitude. In magnitude, they are the same. So the proportionality constant K is equal to 1 over 4 pi epsilon naught. This epsilon naught is called permittivity of free space. Then the epsilon naught is equal to 8.85 times 10 raised to minus 12 Coulomb square over Newton meter square. So K in general, so substitute this value here, 1 divided by this value 4 pi multiplied by 8.85 times 10 raised to minus 12. Finally, approximately you will get K is equal to the proportionality constant is equal to 9.0 times 10 raised to 9 Newton meter square Coulomb square. This is the value. Okay, so considering a system of n point charges, if you have n number of point charges, the net electric force on that given test charge will be equal to Qy, Q0. Q0 is a test charge that we need to consider. I is the number of different charges we may have from 1 up to n charges, so you have to vary this one, and this one also the distance between this test charge and the other Q1. It may be Q1, it may be Q2, it may be Q3. So the force is equal to the K constant should be written outside, and the summation of this value. It's may, for example, Q1 Q0 R1 naught square plus Q2 Q0 over R2 naught square plus, and so on. It continues like that up to n values, and finally you'll get the total net force on a given test charge. The total net force on a given test charge is given by this formula. Okay, example, the force between two identical charges. Whenever it says two identical charges, it may be two positive charges or it may be two negative charges. So the force between two identical charges separated by 1 centimeter, they are separate. The distance between these two charges is separated by 1 centimeter is equal to 90 Newton. So if they are identical, then the force is in opposite direction. For this one 90 Newton in this direction, for this one also 90 Newton in this direction. So the question is, what is the magnitude of the two charges? The question is finding the magnitude of the two charges. Therefore, force is equal to, you know that force is equal to K times Q1 Q2 over R square. So Q1 and Q2 are the same, therefore force is equal to K times Q square over R square. So R square multiplied by F force R square over K constant is equal to Q square. So the square root of force R square over the value of K constant is equal to the charge. So square root plus or minus, we have to use a plus minus sign. Here is the solution. The force is 90 Newton. Q1 is charge of the first body, Q2 is charge of the second body, and the distance between them is 1 centimeter. So using the Coulomb's law, force is equal to K Q1 Q2 R square, then multiply by R square, FR square divided by K, FR square over K. This is FR square over K. Why we make this Q square? Because Q1 is equal to, the two charges are identical, Q, so under square roots, in this case you have to use plus or minus. Q is equal to plus or minus FR square over K. Force is 90 Newton. R is, in terms of it's 1 centimeter, when you change it to meter it becomes 0.01 meter square, and then you have to get approximately 8.89 or approximately 9 times 10 raised to 9 for the values of K. for the values of K, Newton meter per Coulomb square. Okay, Newton meter square, Coulomb square. So finally you'll get 10 raised to minus, inside this 10 raised to minus 12, then outside the square root it becomes 10 raised to minus 6 Coulomb, or it is 1 microcoulomb. So if Q1 is equal to positive 1 microcoulomb, Q2 will be positive 1 microcoulomb. If Q1 is equal to negative 1 microcoulomb, then Q2 is equal to negative 1 microcoulomb, because the two charges are identical. Okay, now let's see the electric field. Qualitatively, electric field can be defined as the region around a point charge particle where all other charged particles experience electrical force. All other charged particles experience electrical force. We have source charge, which is plus Q, and we have also test charge plus Q. So these are the different test charge, and the direction of the force, electrostatic force, is this one. Because of this test charge, we can find the direction of the electric field lines. So the direction of the force, this is positive charge, they repel each other, then the direction of force is away from this charge. So this is indicates this direction, the direction of the force, or it is the direction of the electric field lines. So this example, this animation actually shows when the charge is moving. So these are the electric field lines. So there is a change in the direction of the force because of the electric field lines. So if the direction of motion is this one, then the field lines will have some force, so the force will experience on that. Okay, now let's proceed to the electric field lines. Electric field lines are models for representing electric field distribution over a space around the charged particle. Like different model we use, like Bohr model for atoms. We use just like that. We have to use electric field line models just to make it very easy for understanding. Or you can easily, in order to understand positive source charge, the electric field points radially outward. This is a positive field charge, so the direction of electric field is radially outward from the source charge. And for a negative one, for this negative one, it points radially inward. For the negative one, it is inward, as shown in the figure below. For a positive, it's outward. For negative, it is inward. Okay, so the energy released in a lightning strike, this is a lightning strike, is an excellent illustration of the vast quantities of energy that may be stored and released by electric potential difference. So the energy stored is actually appears because of the presence of those clouds. Okay, so electric potential, when a free positive charge Q is accelerated by an electric field, it is given a kinetic energy. So the process is analogous to an object being accelerated by a gravitational field. If the charge were going down the electrical hill, where the electric potential energy is converted to kinetic energy, like this one. We have a charge here. So when it approaches this one, it has maximum potential energy. When you release the charge, so the potential energy will be changed into kinetic energy when it approaches to the negative charge, because the positive repel the positive one, then the negative attracts this one, so the potential energy will change into the kinetic energy. The other one that we have is the gravitational. So this from higher, this is the potential energy will change into the kinetic energy. So we use minus sign because it is G is equal to the change in kinetic energy. So they are similar with each other. So you can compare one with the other. Okay, so electric potential energy. The work done, work 1, 2 by applied force F when a charged particle moves from point 1 to point 2 be calculated by work is equal to this force. This is applied force, this is the electrostatic force. So when you bring charge from infinity to here, and if there is a distance r between the two charges, therefore the work done will be equal to this, the applied force will be equal to the electrostatic force. So instead of applied force, it's possible to change into the electrostatic force. So the work, in order to bring this charge from infinity to here, so distance is r, so F multiplied by r value will be the work done. So the work done is equal to Fe r cos theta value. This is a dot product between two vector quantities, the force and the displacement. Therefore, then we have to use this scalar quantity plus the cosine, the angle between F and R. So in this case, the angle is 0. The angle is 0. Since the electric force and the displacement are parallel, the angle theta between them is 0. And hence the above equation become cosine of 0 is 1. So F times R. So F is already known, which is K times this Q multiplied by this Q over the distance between square. R square, the distance between them is R. So R square, R cancelled by R. Then finally, work 1, 2 will become, this is Fe, which is K times Q1, the smaller Q and large Q over R square. Then multiplied by R, work 1, 2 is equal to, work sub 1, 2 is equal to, between these two, then it is equal to K multiplied by, then R cancelled by R. Finally, it becomes K small q capital Q over R, or 1 over 4 pi epsilon naught small q capital Q over R between two charges. So the work done on a charge Q is exactly equivalent to the potential energy of the configuration of the two Q1 and Q of system of charges. Therefore, we define electric potential energy of any two system of charges Q1 and Q2 is separated by R1. It is given by this one. Electric potential energy similar to this one, 1 over 4 pi epsilon naught Q1 Q2 over R12 will be electric potential energy. So this is one of the best examples that we have. Find the electric potential energy in assembling 4 charges at the vertex of a square side 1 centimeter, starting each charge from infinity as shown. So all these charges assume that they are at infinity. Then we bring them together to form such structure.